In this video I'm going to talk about some special types of matrices that have some particular properties regarding their eigenvalues and eigenvectors. Okay, so let me start by one type of matrix that you already know, and that's unitary matrices. So you already studied unitary matrices with me, and what you knew is that they preserved the lengths and the angles between vectors, and I also demonstrated to you that the inverse of a unitary matrix is equal to the Hermitian conjugate, or A dagger, of the matrix, right? So these are unitary matrices. Now, another type of matrix, which is actually really common when you study quantum mechanics, is called a Hermitian matrix. So Hermitian matrices. And Hermitian matrices have the property that A is equal to the Hermitian conjugate A dagger. So they are equal to their Hermitian conjugate, okay? So let me give you an example of a Hermitian matrix. Let me give you an example, e.g. So this matrix here. So Hermitian matrices always have real values on the main diagonal, because otherwise the Hermitian conjugate would flip the sign of the imaginary parts of those components, and it would not be equal to itself. So always real values on the main diagonal, like 2, 3, and 1. And then off of the diagonal, it has the complex conjugate of each other. So if you have a I here, you necessarily have a minus I here on the other side. So that when you do the Hermitian conjugate, remember the Hermitian conjugate means you conjugate all of the elements and then you do the transpose of the matrix. So like flip, like a mirror image of the matrix, yeah? So therefore every element must have a mirror image which is equal to its complex conjugate. So for instance, if we had 1 plus I here, then we would have 1 minus I in the mirror image across the diagonal. And if you had a real number here, then the real number would be equal to itself. The complex conjugate of a real number is itself. So this would be an example of a Hermitian matrix, okay? When A is equal to A dagger. And actually, these two types of matrices, both unitary matrices and Hermitian matrices, they form part of a larger group of matrices, which is called normal matrices. And normal matrices are any matrix that fulfills this property, that A times A dagger is equal to A dagger times A. Or in other words, the matrix A commutes with A dagger, okay? Now, it's quite easy to prove that unitary matrices are inside normal matrices. So they are a special case of normal matrix, and let me prove it to you. So A times A dagger, if this is a unitary matrix, this will be equal to A times A inverse, right? Because that's what unitary means. And therefore, this is equal to the identity matrix. And the identity matrix is equal to the inverse times A, which is equal to A dagger times A. So by comparing the left and the right, we can see that it fulfills the condition of being a normal matrix. Okay, so every unitary matrix is necessarily also a normal matrix. At the same time, every Hermitian matrix, if you do A times A dagger, you are doing A times itself, because this is a Hermitian matrix, which is equal to A dagger times A, right? Because A dagger is equal to A. And therefore, comparing the left and the right-hand side, you can see that Hermitian matrices are also examples of normal matrices, okay? So you could think of this as being mammals, and then this is horses and lions, yeah? Every lion is a mammal, and every horse is a mammal, okay? That's why I did this Venn diagram, trying to classify these three types of matrices. Okay, so what are the properties that these special types of matrices have on the eigenvectors? So let me write it here. So if A is normal, it's a normal matrix, and let's say that the size is n times n, then it necessarily has n orthonormal eigenvectors. Okay, this should kind of surprise you. So it's a very interesting property that if A is a normal matrix, it necessarily has n orthonormal eigenvectors. So orthonormal, remember, all of the eigenvectors are orthogonal to each other, and they can also be made to have a modulus a length equal to 1. Yeah. Actually, the length of the eigenvectors is arbitrary, as you know. If an eigenvector is given by the vector 2, 1, any other multiple of 2, 1 is also an eigenvector. So you can always scale the eigenvectors to have unit length or unit norm. But the important part is the the fact that they are all orthogonal to each other. Yeah. So these eigenvectors are always orthogonal to each other, and you always have n eigenvectors equal to the size of the matrix. Okay. Next, what happens if a matrix is a Hermitian matrix? So if A is Hermitian, then necessarily A is normal. Yeah, right? So I proved it to you here. So Hermitian matrices are an example of normal matrices. And therefore, if A is Hermitian, A is normal, and if A is normal, it has n orthonormal eigenvectors. So I can copy this top thing. I can copy it here. Okay? But on top of that, let me draw a line here to separate. It also has another property. So if A is Hermitian, it turns out that all of the eigenvectors are real values. Eigenvalues, I mean. All of the eigenvalues are real. So lambda I is inside the real numbers. Okay? And I will actually prove this in the next video. I will show you a proof. And finally, if A is a unitary matrix, remember an example of this, the rotation matrix was a unitary matrix. Then A is normal, and therefore we can, if A is normal, we can copy the property above that it has n orthonormal eigenvectors, right? Because A is normal. But apart from that, it also has another property, that all eigenvalues have a complex amplitude equal to 1. So if we write it mathematically, the complex amplitude of the eigenvalues is equal to 1. Okay? So that is it. Those are these properties for these 3 types of matrices. Okay? In the next video, I will prove some of these properties. See you.